I will spend a few minutes in this video talking about EMF, and by EMF we use this symbol. It's unclear to me whether this is an uppercase Greek letter epsilon or if it is some kind of unique E, uppercase Latin character E. I don't know, but in any case, this is the symbol we use for EMF. And sometimes you will also see me just writing EMF. Okay, I think most probably you will see me writing EMF rather than this. In any case, by definition, the EMF is a closed path integral. Okay, it is a closed and it is a path integral. This F here, this is the force per unit charge, and of course dot dl. Now I want to talk a little bit about this force per unit charge. You will see that this has two contributions. One due to an electric field and one probably due to a power source, let's say a battery. This is probably the most common thing you will see. And this is the electric field. Now, if let's say this is equation 1, if I use 1 and 2, I get that the EMF is the closed path integral of this sum dot dl. Now, if you have a case where the only charges, no, let me say this again. The only thing that creates your electric field E is if this is E is due to charges. We know that the potential difference, if you do a round trip, is 0. Okay, if you start from one point and you come back at the same point, you just made the loop, we know that the potential difference is 0. And it does not depend on the path. So the closed path integral of E dot dl is 0. Now, I want you to remember this though. This is a true statement. The closed path integral of E dot dl, it is a true statement so long as E is due to charges. Okay, we have seen this, and that's why in the book you may see that EMF is the closed path integral of Fs dot dl, because you see that the closed path integral of E dot dl is 0. I just want you to remember there is, okay, when we talk about a little bit later in the class, when we talk about changing electric fields and changing magnetic fields, we will encounter a case where the closed path integral of E dot dl will not be 0. Okay, so far you have seen what properties the electric field has, in electrostatics, But as we're moving on and we start dealing with changing electric fields and changing magnetic fields, we will start also include in our discussion what I call the non-Coulomb this is, okay, where you see NC, this will be the non-Coulomb electric field. If the electric field is due to charges, then this will be the Coulomb electric field, where this is true. But we will soon see that we also have, in some cases, we also have an electric field created that is not due to charges. It is not, charges are not responsible for the presence of that electric field. And this is the one that I'll be calling the non-Coulomb NC electric field. For that electric field, the closed path integral is not zero. So what I want you to remember is that, okay, this is the definition of the EMF. And we can break that force per unit charge as a sum of two terms, the electric field and another term that may be due to a power source. Now, if you combine the two, of course, you're going to get this expression. Just don't assume that the closed path integral of E dot dl will always be zero, because it will not.